Okay, we'll get started here. It is Friday. Happy Friday, everybody. And it's the end of 8th week. So we'll get through today's lecture here. Hang on, let me turn on my turn on the view quiz for today. And okay. All right. The today's topic is the EM algorithm, and we'll look at kind of a specific application of the EM algorithm for Gaussian mixtures. Technically, the EM algorithm can be extended to any kind of clustering data set where you have some missing variable for like how the data, which observations it should belong to. Okay, maybe on the outset, I will say the EM algorithm. Oh, are the notes posted? I forgot to post the notes. Sorry. Let me post these notes. One moment, please. Okay. The EM algorithm is kind of a cross between k-means clustering and the Bayesian classifier, right? So we learned the Bayesian classifier, which gave probabilistic assignments for which, to kind of which class an observation belongs to. And then you have k-means clustering, which kind of takes points and assigns it to, a particular cluster. And, k-means clustering uses Euclidean distance. The EM algorithm is kind of like that, where you're going to do probabilistically assign points to a cluster. And then what you'll do is you'll kind of recalculate not the centroids, but kind of properties of each cluster based on the points that are quote unquote assigned to it, even though it's done in this probabilistic sense. So let me just kind of start off with creating a Gaussian mixture, okay? And so a Gaussian mixture is basically, you're gonna have some points, a distribution of points, and the points themselves come from a mix of different multivariate normal distributions, okay? So here I'm gonna have 3 multivariate normal distributions, and we're gonna say points will come from cluster 1 or distribution 1 with a probability of 50%. They'll come from distribution 2 with a probability of 30%, and they'll come from distribution 3 with a probability of 20%. All right, and these are the properties of my 3 different distributions. So distribution 1 is the largest one with 50% of the data, and it is going to be centered at 0, 0. And it has, and its x1 and x2 variables are independent of each other. The off diagonals of the sigma matrix are 0, and it's got large variance with variances of 9. Okay. Distribution 2 is centered at 4, 4, which you kind of think of as the top right corner with this matrix, and so there's high covariance between x1 and x2, right? And then distribution 3 is centered at -4, -4. So you think of that as kind of the lower left corner, and its variance is this, and there's negative covariance between x1 and x2, okay? And so let me plot this. This is going to be kind of what the distribution of the mix of 3 distributions will look like, okay? Let me kind of go back. And so mathematically, we're going to say the values within some x, okay? Okay, so this is some point in 2-dimensional space, okay? Given all of the parameters, right? And the parameters includes basically everything here. The mean vectors of the 3 distributions, the sigma matrices of the 3 distributions, and the alpha vector showing the proportions of each distribution. So there's a whole bunch of parameters, and they're all going to be gathered into this big theta, okay? So to kind of say all the parameters from all the different mixtures, including the the mixture weights, okay? And the probability of any one point is going to be the sum of three products or three kind of probability densities, okay? So you have the multivariate probability distribution, which is this P sub k, right? That's just going to be the multivariate Gaussian PDF. So you just think of that as the normal PDF, okay? But for multivariate thing, okay? Multiplied by the mixture weight, right? So you take, distribution 1, multiply that by 0.5, you take distribution 2, whatever, the PDF of this distribution, you multiply that by 0.3, and you take the density or the PDF of distribution 3, and you multiply by 0.2, and you add all of them up. And that's going to be kind of the overall probability that, one observation has, okay? And so that's going to be kind of it's the probability density function for each of your different k components all added up, right? And then you also have an indicator variable to kind of indicate that, some observation belongs to a certain cluster or not. Okay, so to kind of generate this in R, I create a vector alpha for my different proportions, 0.5, 0.3, 0.2. I create my mean vectors, mean 1, mean 2, mean 3, and I create my sigma matrices, sigma 1, sigma 2, sigma 3, okay? And I'm going to gather them together into a list of means, and I gather them together into a list of sigma matrices. And then I'm going to generate a whole bunch of values, not a whole bunch, 1,000 of them, okay? I'm going to generate 1,000 values. And the way we're going to do this, okay, is first I'm going to sample a value k, right? K is going to be either 1, 2, or 3. And the probability that it's 1, 2, or 3 is going to be based on alpha. So it's going to be 1 with probability 0.5, it's going to be 2 with probability 0.3, and it's going to be 3 with probability 0.2, okay? So first we're going to generate k, which will indicate which class it's in. Is it in class 1, class 2, or class 3? So here I'm generating the data, okay? And then once I've determined which class we're in, I'm going to generate one value from the random multivariate normal distribution, okay? So we're going to say random multivariate normal. I want one value, and we're going to say use the mean that corresponds to distribution k, and use the sigma matrix that corresponds to distribution k, because remember, those are gathered here in this list for means and sigmas, okay? So we're going to, this will be a mean vector, and this will be a sigma matrix, okay? And so this will be, the random multivariate normal will generate a two-dimensional coordinate plus the, and then we're also going to include the cluster k belongs to, okay? And then we're going to store that into our X matrix, right? And we're going to do this 1,000 observations. Okay, and so this is the plot of just the X1 and X2 coordinates, okay? And so here, this is just how the data is going to appear. And here the clusters are not labeled. This is just how we see the data, okay? So they come in variables X1 and variable X2. And this is it, okay? And what we want to do, all right, so we generated the data. We know where, which cluster each of these observations belong to. But what we want to do with the EM algorithm is we want to cluster the data points, okay? We want to say, do certain points belong to, one cluster or another cluster or another cluster, okay? And we don't want to just do this using Euclidean distance. We don't want to use k-means clustering because we want to kind of allow for, one distribution to have a big variance and another distribution have different variances and stuff, okay? And so, this is the data labeled, and we can say, oh, okay, we've got a whole bunch of points coming from cluster 1, which is in black. We have a bunch of points coming from cluster 2, which is in red, and we have some points coming from cluster 3, which is in green, okay? And so we can see, there's overlap between these different clusters, between black and green, there's overlap. Between black and red, there's overlap. And what we kind of want to do is we want to, still we want to cluster these points. Okay, so these here we've labeled it. Usually these assignments are unknown to us. We're going to kind of cheat in that, like, we've generated the data, so we know where they're coming from. But again, normally this is how you see the data. You just kind of see this and you want to try to identify some kind of structure or some kind of clustering here using the EM algorithm. Okay, and so, we look at this, right? And so let's say we look at this point right here, which is kind of on the edge between, we might just visually, we can see this point belongs, there's a cluster here, and then there's also kind of the large cluster. And so the question is, if we zoom in on, say, one of these observations here, how should we do this? Okay, how should we assign this point to a cluster? Okay, so under k-means clustering, you just kind of said this is going to get assigned to the nearest cluster. And with the EM algorithm, we want to be a little bit more nuanced than that. We want to just say, you know what? If you told me this was part of the big cluster in the middle, I would believe you. If you told me this was part of the cluster over here, I would also believe you. And so, whereas if you told me it was part of this cluster, I would not believe you, right? So we want to kind of give it a little bit more of a probabilistic thing. So we're going to say, you know what? A point right here might be 50% cluster in the middle, 50% cluster over here, and 0% or point, something almost close to 0% that it's going to be a cluster right here. Okay. So we want to do a probabilistic cluster assignment rather than just some kind of hard rule and saying this is the cluster, or something like that. Okay, let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is the letter E. E as in elephant is our first view quiz answer. All right, and so this is basically what I said, is that we're going to use a probabilistic assignment. So rather than strictly assigning a point to one cluster, like we did in k-means clustering, we're going to use a Bayes classifier to get a probabilistic assignment. And that probabilistic assignment we're going to call a membership weight. Okay, so each point is now going to have a vector of probabilities, and that vector of probabilities is going to sum to 1. Okay, and so once you have those membership weights, you can calculate. What we're going to do now is we're going to calculate the parameters of each cluster distribution. This is kind of like finding the centroid of your clusters, except there's more to it. We're not just finding the centroid, which would be the mean, but we're also going to try to estimate the variance matrix, that sigma matrix. We're going to try to estimate that. So what we're going to do is we're going to estimate the mean by using a weighted mean. So values that belong to, that have a high probabilistic assignment to a particular cluster, those will be counted heavily in the calculation of the mean. And values that have a low probabilistic assignment of belonging to a cluster will have a low weight, right? So when we're talking about, finding the mean of this green cluster, points out here are going to have very low probabilistic assignments to the green cluster. So they're going to have very little influence as far as determining where the mean of this green cluster is. Okay, observations over here are going to have a high probabilistic assignment to the green cluster. So when we estimate the mean of the green cluster, we're going to weight those heavily, and we're going to weight these ones out here less heavily, right? Similarly, for the red observations, observations out here will have low probability assignments here, so they will influence the mean of this thing very little, whereas observations close here will have high influence. We weight the estimates of the mean accordingly. Okay, and similarly, we're also going to estimate the sigma matrix, the variance covariance matrix, by also weighting the observations accordingly using the probabilistic assignments. So using the membership weight, values out here will influence the sigma matrix of this red cluster heavily, whereas, observations out here, they're not going to really influence the sigma matrix here. Okay, and we do this and we iterate back and forth, kind of like the k-means clustering algorithm, between recalculating your membership weights and recalculating the parameters of the cluster distributions. Okay, so calculating your membership weights is known as your E step, your expectation step. Recalculating the parameters of the cluster distributions, which would be calculating the mean and calculating the sigma matrix, will be the M step. All right. And again, we can think of the EM algorithm as kind of some kind of blend between k-means clustering and the Bayes classifier. All right, does this kind of make sense from some high level perspective here? Okay, all right, so again, when we calculate the membership weights, we're going to calculate it using a Bayes classifier. And so, we're going to say, given the X values that are stored in the point, okay, all of the parameter values, that is, I'm sorry, given the X values in the point and all of the kind of parameter values, the mean and sigma matrices of the clusters, we're going to calculate our membership weight, right? And so we're going to do this by doing the likelihood times the prior divided by the marginal. And again, just like when we did for the Bayes classifier a couple weeks ago, the marginal, the denominator, is just found by taking the numerator and summing it across all possible clusters. So in our case, we have 3 possible clusters. We're going to calculate the numerator across all 3 possible clusters. And the sum of that is going to form our denominator. And that's going to have the effect of taking the numerator and scaling them such that when you add up the numerator, they're going to add up to 1, right? When you add up the numerator across all possible classes, it's going to add up to 1. Okay, and so this part, this is the PDF of, we're going to get this using the PDF of the normal distribution using the current estimate of the mean and sigma matrix. And then your prior is just going to be your alpha, okay? The alpha here is the probabilistic, basically the membership weights, okay? How many points belong to a certain cluster. So when we talk about this thing, we're going to say how many points belong to cluster K? How many points belong to cluster 1? How many points belong to cluster 2? How many points belong to cluster 3? The tricky thing here is that the number of points that belong to cluster K is not going to be an integer, right? So with k-means clustering, you just had certain, you assign points to a cluster and that was it. But here we get probabilistic assignments. And so, this observation, maybe has a 99% chance of belonging to cluster 1. And this observation has a 20% chance of belonging to cluster 1. You're going to add those together and you're going to say 1.19 observations belong to cluster 1. Okay, it's a little bit of a weird thing, but you're basically going to sum up the weights of all of the observations that belong to a certain cluster. Okay, so the number of observations that belong to cluster K is going to be the sum of the weights, and that's not necessarily going to be an integer. Okay, it's almost certainly not going to be an integer. All right, but we're going to use that to get this, and then we divide by n, and we're going to get, how many quote unquote points belong to cluster K, cluster 1, how many points belong to cluster 2, and how many points belong to cluster 3. When you add all of those up, you're going to get the total number of points. They will add up to how many observations. If we have 1,000 observations, the sum of the different, the sum of the different alpha Ks will add up to 1, right? So if you do the number of, we might say, 522.7 observations belong to cluster 1, 283.6 observations belong to cluster 2, and then some other number belongs to cluster 3. And when you add up all of the NKs, it's going to add up to N, okay? Because all of the WIKs will all add up to 1 for every observation. And so when you sum up all of the NKs for the different groups, they're all going to add up to N as well. Is that okay? membership weights, getting this kind of this prior, the value over here. Okay, it's the prior probability, based on the previous iteration that a point belongs to cluster K. And it's the number, it's the proportion of points assigned to cluster K. Whereas, the number of points assigned to cluster K is not really the number of points, it's some non-integer sum of weights. Okay. So that's going to give us our membership weights, right? And then here, the likelihood, this likelihood is going to be equal to the probability density function for the values in X given the cluster's mean and sigma matrix, right? So we're going to say, what is the likelihood this observation came from cluster 1 if our estimate of cluster 1's mean is this and our estimate of cluster 1's sigma matrix is this, right? And I think we did something very similar when you did your Bayes classifier in your homework, okay? Actually, in the homework, it was the naive Bayes classifier, but effectively in the lecture, it was something very similar, except in the homework, you had a product of normal distributions. Here, we're going to just use the multivariate normal distribution directly, all right? So we're going to estimate the likelihood of some observation belonging to cluster K, given its, values in X, and the current estimate of the mean for cluster K and the current estimate of the variance or sigma matrix for cluster K. All right, so that's going to give us the likelihood. Is that all right? Okay, and so that's going to give us that. And so that will give us kind of all of the estimates for, we use that to calculate the weights, right? So we go through, you calculate your alphas, you calculate your likelihoods, and then you get your denominator. And once you do that, you can get your weights. You can get your membership weights, WIK. So you do this for all of the observations, okay? And then once you've calculated your membership weights for every point, we say, what's the probability this point belongs to this cluster and probability of this point to the other clusters and stuff, we have to recalculate the centroids or the means of each cluster. And we're going to have to recalculate the sigma matrix of each cluster, right? And so it's an iterative process of calculating membership weights and then recalculating distribution parameters. And then we go back, recalculate membership weights, recalculate distribution parameters. All right, so the mean is basically going to be the weighted mean of the observations that belong to the cluster, okay? So we're going to take X sub I. And so before, when we had k-means clustering, the mean sub k was the product of zik, which was just a 0, 1, if that point belonged to the cluster or not. And now it's basically the same idea, except instead of a z, which is a 0 or 1, it's a weight, which is going to be a number between 0 and 1. It's going to be some decimal value between some fraction between 0 and 1 that indicates the probability that X belongs to cluster K. Okay, so we do that. We're going to add up the weight times each X, and then we're going to divide by how many observations, quote unquote observations, belong to cluster K. All right, so again, this n sub k is not really an integer. It's just how many, the sum of the weights that belong to cluster K, and then that's how we're going to calculate the mean of cluster K. All right, so it's just a weighted mean of the points that belong to X. All right, so points that are highly likely to be in cluster K will have a membership weight close to 1 and will contribute more to the calculation of the mean. Points that are unlikely to be in cluster K will have a weight close to 0 and will not really affect the value of the mean very much. Right, and then the last thing is going to be calculating the estimate of your sigma matrix. Okay, and this effectively boils down to just a weighted version of getting your sigma matrix, right? So if there were no weights, and we just said, you know, what's the sigma matrix of some set of observations, you would just do x minus mu transpose, and then you divide by well, the MLE you divide by n, and then the other you divide by n minus 1. Okay, here we're going to basically do something similar, except each contribution of x minus mu times x minus mu transpose is going to be weighted by its membership weight. Okay, and we do that, and then we divide by n over k. So same idea, except we're doing it to calculating the sigma matrix. All right, I just want to kind of pause here and just make sure this feels good with everybody, or if there's any questions as far as any of this stuff goes, like where the membership weights are coming from, where the estimates of these things are coming from. And my hope is if you understood the Bayes classifier, these steps over here make sense. And if you understand how we calculated the mean in k-means clustering, that this makes sense, except we're just changing it from a z to a w instead of 0, 1, where it's now some value between 0 and 1. Okay, so if that's good, let me go ahead and give you your second view quiz answer, which is the letter C. C as in cat is your second view quiz answer. C as in cat. Okay. So now I've got a bunch of pictures that just show kind of how the algorithm will work, the EM algorithm will work. All right. So again, our data come in totally not labeled. And we just kind of have to start our algorithm using some arbitrary starting values. And so a lot of times for, and these are the true labels, okay? So a lot of times you just have to kind of start off with some arbitrary starting values, all right? And so here, I'm going to start off with 3 possible means. I'm gonna start off with alpha equal to 0.33, 0.33, and 0.34. This is just an arbitrary starting thing. We're gonna just say, at the beginning, our data has a 1/3 chance of belonging to each cluster. And then I've got 3 means, 0, 0, -9, -9, and 9, 9, okay? So this is a little bit different from k-means clustering, where you started off with random assignments of points. Here, we're gonna start off with random parameter values, random starting parameter values. So I'm gonna say, I'm gonna just guess the mean is this, and I'm gonna guess that the centroids are here. We're also going to just start off with some arbitrary variance covariance matrices. And here I'm just putting in the identity matrix for our starting sigma matrices. Okay, and I've hidden the rest of my code because you're going to code up the EM algorithm as your homework this week, right? So that's part of your homework. I hope it's satisfying when you get your algorithm to work. And again, so this is what we're going to do. Okay, so this is kind of what my starting picture looks like. All right, and so here I have this is the normal distribution. These are contours of the normal distribution here. And the centroid is here at 9, 9. The centroid is here at -9, -9. And this centroid is at 0, 0. And then so we just ask probabilistically, where do these points get assigned? Okay, now this picture is misleading. Okay, this picture is misleading because the truth is every data point gets a probabilistic assignment. Okay, and here, as far as the coloring goes, I can only really color a point as either black or green or red, or some color. And I mean, I guess I could have tried to find some gradient thing, but the truth is if you zoom in on these observations here, this observation is not green and this observation is not black. It's like 51% green, 49% black. And this one would be 51% black, 49% green, okay? But as far as getting represented in the graph, I just had to pick a single color, okay? Similarly, if this represents the centroid of the red cluster, okay, basically all we're doing right now is we're just drawing a line halfway through between, this center and this center. I'm just drawing a line halfway through, and I'm saying, okay, well, this observation here is 51% black. This one is observation here is 51% red. And so they just get colored as red or black, okay? But the reality is it's not red or black. It's, as the picture would indicate, these are all probabilistic assignments, okay? The ones in the center will be, probably 99% black over here. And, these ones right now would be like 99% green, and observations out closer to here would be 99% red. But again, everything gets a probabilistic assignment. And so it looks like these are just kind of clustered to one thing or not, but everything is probabilistic, okay? And I think I write this on the slide, okay? So again, points on the border are, 51%, 49%, red and black, or 49% red, 51% black, but they're represented with a single color. So that's something that we have to keep in mind, okay? But so we start off here, okay? And then we look at this and we say, okay, based on the points that have been assigned to green, and again, probabilistically assigned to green, what is the new centroid of all of the green points, okay? And again, we are considering anything that is probabilistically assigned to green, which is going to include these points out here as well. Anything that has a probabilistic assignment to green, we're going to use those to calculate what the centroid of the green points are going to be, right? So at the next iteration, we say, okay, we update and we say, all right, the new centroid of green is going to be here. The new centroid of red is going to be here. We calculate using these points. We say, well, what would the sigma matrix of green be, okay? And the sigma matrix of green, based on those observations, would look like this. What's the sigma matrix of red? It's going to look like this, okay? It's going to kind of give us this shape. And then what's the sigma matrix of the center, the cluster with the black points? And because the central cluster contain, so many points, its sigma matrix estimation is going to be huge, okay? And so now we have kind of these three distributions, and we say, based on that, reassign the points probabilistically to either green, red, or black, okay? And again, when you look at the border region between, what's red, what's green, and what's black, and what's red, and what's black, these are all probabilistic, okay? And so these contour lines are kind of trying to show the elliptical thing, right? Is that okay? Are there any questions on this? Okay, and then so again, we have new probabilistic assignments, and then we're going to recalculate our probabilistic weights, okay? So, so we go from here, and we do here, okay? And then again, we reestimate the centroid and the sigma matrix. We reestimate the centroid and the sigma matrix. And so you can see these things are refining, and then, we continue. And after more iterations, this is effectively where, so if I scroll through this, it forms a nice, almost like a nice little animation of what's happening, right? Okay. And so at the end, this is kind of the final clusters that result at the end. Okay, and again, these are all probabilistic assignments. It's hard to see the probability when you're representing it with a single color, but again, these observations here near the border between the red and the black are probably like 51% red, 49% black, or something like that, okay? And so, so this allows us to do clustering, not based only on Euclidean distance, but taking into kind of the idea that some of our distributions could have much larger variance matrices, allowing for different kinds of variation and things like that, okay? All right, and so that's the result of the EM clustering, EM algorithm searching for clusters, okay? I kind of want to, and if you compare this with the true groups, this is what we have. And again, here we ended up with green over here and red down here. Again, the labeling is arbitrary. And so, what gets labeled to what doesn't really matter. And we can see, in the true groups, some of these points out here came from black and green. Some of these points out here came from black and red. But when you do the EM, this is just probabilistic. And so they say, it's more probable that all of the points here came from green rather than black. And so all of these colors, all of these points get colored green, okay? But again, it's probabilistic. It's probably like 80%, 70% green and black and stuff like that. And it's more probabilistic for all of these points to have come from the red cluster than the black cluster. And so they all get kind of colored red in these pictures. Okay. The EM algorithm is sensitive to the starting locations that you use, okay? So here I'm going to intentionally pick some some different starting locations, okay? And so here we're going to do 0, 0, 0, 10, 0, negative 10, okay? And so these are kind of the initial assignments as far as where the centroids are, or where the means are, and where the and I'm still using kind of identities for the identity matrix for the sigma matrices. Okay, and then so we go through, and if you allow this to kind of work through, okay, this it managed to kind of find the correct answers. Oh, I have another example though. I guess I didn't put it in my slides or it doesn't necessarily work out. So if you start off with some bad starting values, you can end up, kind of with bad clusters as well. All right. And so a lot of these things are subject to what your starting values are. So k-means clustering, what your initial random assignments are, can end up influencing where the points end up. And same with the EM algorithm, where your initial kind of starting guesses can influence where they end up. Okay. There's a similar animation on the Wikipedia page for the EM algorithm. All right, and so this is an animation for old faithful eruption data. Okay, so I guess they measured how the duration of the old faithful geyser in Yellowstone, how long the eruption was and how much of a delay there was between one eruption and the next eruption. And apparently, if you search for two clusters, you get kind of this resulting thing. And so again, they just started off with some arbitrary things and initially, and they kind of identified two clusters. What this means, as far as the interpretation of the data, it's a little bit hard to say, but perhaps there are different kind of geological processes that that influence exactly when the eruptions happen. Okay, we have a question that says, is that why for k-means it runs the algorithm 20 times to account for random seeds with k-means in R? Yeah, so when you run k-means in R, its default behavior is to do a whole bunch, several different what do you call it? Yeah, several different starting seeds to see different kind of possible possibilities that could happen. And so so the hope is that if you run a whole bunch of these different things, a lot of them will end up with the same clustering assignments at the end. and then you can kind of go off with the ones that ended up most common or most popular as far as these multiple different starting seeds went. And as far as the EM algorithm, yeah, you can just start off with different arbitrary starting seeds. You can kind of, if you have a general sense of the data itself, you can try to put in some educated guesses for what your starting seeds, or starting centroids and starting sigma values could be, to kind of help guide the search for these things. Okay. But yeah, that's the EM algorithm. I hope there's enough instruction or guidance in the homework to kind of guide you through that process of coding this up. Okay, that's all I have planned for you guys today. So we can end here. The last view quiz answer for today's lecture is the letter B. B as in bear. B as in bear. I gave you the other two, right? Okay, great. Okay, so we'll end here. Have a good evening. Have a good weekend. We'll see you guys on Monday.